Hello everyone. Can you hear me? Type something in the chat. Okay, perfect. Okay, so finally, we have in physics we've completed the mechanics section. So everything from now on is not related to mechanics, and we start with direct current or DC electricity. So quite an interesting topic. So I have published the unfinished version of the assignment. Okay, so very sorry that it's taking so long to do. We're just making the final amendments. It will be very similar to what is there. So you can have a look in the you know what I mean, on the whiteboard, on our whiteboard. So I'm going to share my screen and let's get to it. So I'll just open the chat. Okay, so you can see what you're doing. Right, so here's the assignment. It's going to be very similar to that. There's just a few changes coming up. The first thing is the due date. The due date will be the 3rd of April. So you have an extra week as promised. So the due date. And yes, so we are talking about electricity. And today I'm going to talk about Kirchhoff's laws and the networks of resistors. So this is the topic for today. I won't be focusing on resistivity or Ohm's law. I'm sure you can figure it out on your own. But I'm going to do some very nasty questions on resistor networks and Kirchhoff's laws. Okay, so let's get to it. So looking at the problem 1, this is an infinite chain of resistors. An infinite chain of resistors, and you need to find the total resistance, of course, in terms of R. So how do we even approach this problem? Well, look, if it's an infinite chain of resistors, then adding another pair of resistors won't change the total resistance. Right. So we have the infinite chain. So copy and paste. And let's say this chain of resistors has resistance R1. So the whole thing has resistance, well, the whole thing has resistance R sigma. Yeah, the total, as in total, R sigma. So what we do is we add another chain, another pair here. We add another pair of resistors here. And since it is an infinite chain, the total resistance is still going to be the same. So the total resistance won't change. It's going to be R sigma. Okay, so let's simplify this diagram. So we have a resistor R. We have another resistor R. And we have the infinite chain. And the infinite chain has resistance R sigma. And of course, you can see the infinite chain is connected here in parallel to the R resistor. And so the resistance between points A and B is the same as, is going to be R sigma. So this is a parallel combination. And for a parallel combination of two resistors, we use the formula R sigma divided by R plus R sigma. Now, this is the parallel combination of these two. Plus R has to equal to R sigma. Okay, does everything make sense so far? Type a number from 1 to 10, please, if you understand what's going on up to here. Okay, a couple of 8s. A couple of 8s. Okay, so this infinite chain I've just replaced with a resistor R sigma. This is the resistance of the infinite chain. And connecting this infinite chain of resistors into here does not change the total resistance. So the total resistance of this combination is going to be R sigma, the whole thing. Okay. So the ones that wrote 8s, does it make more sense? Is that 8? Is that 8 now a 10? Okay. So that's clear. So the infinite chain, the original infinite chain, has resistance R sigma. So what I'm doing is I'm replacing it with just a single resistor with resistance R sigma. And I'm connecting it to another chain link, this one. And because it's an infinite chain, the resistance won't change, because if you're infinity plus 1 is still infinity. All right, so here, and this might look horrendous, but it's not. It's a quadratic equation. So I'm multiplying by R plus R sigma. Sorry for the mess. So it's going to be R sigma plus R squared plus R sigma. Oh, okay. That's a good question. Sorry, I thought everyone knew that. So you have, if you have a parallel combination of two resistors of R1 and R2, so 1 over R total is equal to 1 over R1 plus 1 over R2. So that's going to be R1 plus R2 divided by R1, R2. So our total is R1, R2 divided by R1 plus R2. So for two resistors in parallel, you can use this formula. Except extreme cases when one of the resistances is infinite. So that's how I got it. So this is a parallel combination, and the combination of this pair of resistors is this. So I'm using that formula. Okay, and now I'm simplifying that by multiplying by R plus R sigma. So, and that's going to be equal to R sigma plus R sigma squared. And what can we simplify? Well, we can cross these out. R squared sigma equal minus R sigma minus R squared equals 0. It is a quadratic equation in terms of R sigma. Sorry, just a second. Very warm. A quadratic equation, you can solve this quadratic equation using the formula. I'm gonna just show you another trick you could use here. I'm going to divide everything by R squared. So I'm going to divide by R squared. And that will make it R sigma divided by R squared minus R sigma divided by R minus 1 equals 0. So I'm going to make a substitution. Substitution U is going to be R sigma divided by R. So U squared minus U minus 1 equals 0. Okay. And I'm going to complete the square here. U minus a half squared minus a quarter so it's equals 5/4. I hope you all can solve quadratic equations. So U is equal to a half plus or minus √5/2. Now, could it be 1 minus √5? Well, it's not, because then it's going to be negative. So U is equal to a half plus √5/2, because it has to be positive. And then we reverse substitute. So R sigma divided by R is equal to a half plus square root of 5/2. So R sigma is a half plus square root of 5/2 R. And that's it. That's the answer. It would be very embarrassing if if this question was on the assignment. No, it's not. I don't remember putting it there. Okay. So that's that. That's the total resistance. That's the total resistance answer. So R sigma is equal to 1/2 plus square root of 5/2 sigma R. Okay. So this one, the second one, is very similar. It's just with a few extra steps. Since we spent quite a lot of time doing the first one. Well, yeah, actually, I'm going to do it. I'm still going to do this. Okay, so what's the problem here? Well, the problem here is that the first link is not identical to the second one. So let's cut it off. Oh, not like that. Let's cut off the link. like that. And let's say that this resistance, the resistance of this infinite chain, is R1. R1. So we can rewrite this link. We can rewrite this chain, this combination with R over 2 and R and R1. On the other hand, if we add another chain in between, if we add an extra pair of R and NR, so R over 2 and NR and R and NR and R, and then we add R1, it won't make any difference. So let's look at this section, because we know that the total resistance of this is R1, which is the resistance of the infinite chain, except the first link, except the first pair of resistors. So I'm going to use this a very similar approach. So I'm saying that NR and R1. So the combination of these two resistors, divided by NR plus R1 plus R is equal to R1. Yeah, because we know the total thing is R1. Multiplying by NR plus R1, so you get NR R1 plus NR squared plus R R1 equals NR R1 plus R1 squared. So NR R1 cancels, and we have a quadratic equation: R1 squared minus R1 minus NR squared. With the same substitution as in the previous one, I have U squared minus U minus N equals 0. And in a very similar way, I have U minus a half squared minus equals a quarter plus N. In other words, U is equal to a half plus or minus square root of a quarter plus N. In other words, R1 is equal to this thing, 1/2. Now, it's going to be plus, because if you notice, minus will give you a negative value. Resistance cannot be negative. So it's going to be plus square root of 1/4 plus N and multiplied by R. Okay, so once we have this, we can move this here and say, okay, that is really cool. Now, what we're going to do is look at this, looking at this circuit. So here I have R total, so R sigma is going to be equal to R over 2 plus the combination of this, which is N R R1 over N R plus R1. Now, but this really reminds me of something. This really reminds me of something, and that something is here. Would you look at that? I already have this fraction, which I really don't want to simplify again. I notice that this is here, so it's R1 minus R. So I have R sigma is equal to R over 2 plus R1 minus R. Okay, so in other words, that's R over, it's minus, so it's going to be R1 minus R over 2. It simplifies to that. And R1 is 1/2 R plus square root of 1/4 plus N R minus 1/2 R, which conveniently cancels. And we're left with R multiplied by 1/4 plus N. And that is the answer. Okay. Any questions here? How well do you understand problem number 2 on a scale of 1 to 10, please? Good. Very nice. Yeah, absolutely. Absolutely. Having done question 1, it is definitely easier to follow. I think throwing you into question 2 would be just cruel. Right. So this one. Find the current flowing through AB. Now, this is where we need to use Kirchhoff's laws, Kirchhoff's rules, Kirchhoff's laws, Kirchhoff's circuit laws. They have many different names, but essentially, you've probably heard about them. The total current flowing into a junction is equal to the total current flowing out of a junction. Or there's another way of saying the total algebraic sum of currents flowing into a junction is 0, which is the same. Current flowing in is equal to current flowing out. It comes from the conservation of charge. So there are 4 junctions here. And let's start labeling current. Now, I'm going to label this current as I0, because why not? This current is going to be I1, I2, okay, I2. This is going to be I2. Now the current that we need, now we don't really know which way the current goes. My best guess would be that the current flows up, because this resistor, the current that let's say the current approaches the junction B. it has a choice whether to go through resistor R or through resistor 2R. And the current is more likely to choose resistor R. Therefore, you would see more electrons passing, well, not electrons, but more charge passing from B to A. But let's say I did not do this observation. Let's say I have no idea which way the current is going. And what I'm going to do is I'm just going to guess. I'm saying, okay, current between AB is flowing downwards. And that's not a problem. I mean, if I get a negative answer, that means my guess was wrong. So I3, and now here I go, this is going to be I4, I5, and finally, this is I0 again. So using Kirchhoff's laws, I can, for the 4 junctions, I mean, you could write it. So I'm just going to write it. So I0 is I1 plus I2 plus I2. So this is Kirchhoff's first law. Although obviously there's going to be 4 equations and not all of them are necessary, but I'm just going to write them out for the sake of it. So I3 for junction A, for this junction, I1 is I3 plus I4. For junction B, it is I2 plus I3. So the current flowing into a junction is equal to the current flowing out of a junction, I5. And finally, for the last junction, I4 plus I5 is equal to I0. We are not going to use all of these equations, but they're just there for the sake of it. So we can use any of them if we need to. Now let's look at Kirchhoff's laws. And interestingly, for the Kirchhoff's second law, the Kirchhoff's second law, as you should know by now, the sum of voltages in a closed loop around a circuit is 0. Okay, the sum of voltages around a closed loop is 0. Okay, so let's take a loop and maybe, oh, let's take this loop. The voltage across this resistor, the voltage is I2R, and the voltage across this resistor is I5R, I52R, current times voltage. So for Kirchhoff's second law, for this loop, I'm going to write that I2R plus I5R, and because so on the resistor, I'm labeling the terminals I1. So current goes from plus to minus. We are going from plus to minus. Now here it's minus to plus. So because we are going around the circuit clockwise, the battery is going to have a negative sign because it's from minus to plus, and this is going to be 0. In other words, EMF is equal to I2R plus I5-2R. Now, I'm going to take another loop, and I can choose any loop. And I'm going to take this one. Now, here current flows in like this from plus to minus. And here from plus to minus. We need to choose. So let's say we're going clockwise around the circuit. So if we go clockwise around the circuit, so for the green loop, so this is the red loop. This is the red loop. And this is the green loop. So, look, honestly, Kirchhoff second law is a bit clunky at times, but once you get the idea, you start understanding how it works. So this one is the voltage on here is I1R. So it's going to be I1R, and because we're going from plus to minus, it has plus. And now when we reach this one, we go from minus to plus. Yeah, plus is where the current enters, minus is where the current leaves. So minus to plus, it's going to be minus I2R equals 0. Okay, you could always just say that because they are in parallel, the voltage is the same, which is good enough. So I1R is equal to I2R. So from here, I1R is equal to I2R because the voltages are the same, and therefore we can simplify that, and we see that I1 plus I2 is equal to I2. I1 is equal to I2. So the currents are the same. Now for this one, for the, let's say we draw a purple loop. Draw a purple loop. So Kirchhoff's second law for any loop in a circuit. So minus plus. So for the purple loop, we have I4R minus I5 2R is equal to 0. Or in other words, I4 is equal to 2 I5, which is completely understandable. I4 is equal to 2 I5. The current chooses to go preferably through the top resistor rather than the bottom one. So I4 is greater than I5, 2 times greater. Okay. The last thing I'd like to do is find the total current, I0, because if you're able to find the total resistance, you can find the total current. That's a little bit of a shortcut, because theoretically you can solve these 9 simultaneous equations and you will get all the values. But that's a bit too much, because the only unknown is I0, I1, I2, I3, I4, I5, and I6 are the unknowns. EMF and R are deemed to be known. But anyways, I'm talking too much. You could solve these simultaneous equations, but I'm gonna shortcut this. So I'm gonna find the total resistance. So the total resistance now. So this is a parallel combination of, well, R and R is R over 2. Is R over 2. You understand that AB plays no role, so you can just join them. So what you have is, you can draw this like this, R, and R. And then you have R and 2R. 2R. And so the resistance of this is R over 2. R over 2. And the resistance of this, well, using the same formula, 2R times R, it's a good 2/3 2R over 3. So plus 2R over 3, which is 3R plus 4, which is 7R over 6. 7R over 6. So the I0, the total current, is the EMF divided by the total resistance, which is EMF divided by 7/6 R. So it's 6 EMF divided by 7R. So that's the total current in the circuit. And that's a very useful thing to do, because as you can see in a bit. And immediately, because I1 is equal to I2, I1 is equal to I2, and we know that I1 plus I2 is I0, we can immediately figure out that I1 is equal to I2 is equal to half of I0, because I0 is I1 plus I2, and therefore each of them is half of I0, which is 3 EMF divided by 7R. And finally, we have I4 and I5. So we know that the sum is I0. So from here, we can say that I5 plus 2I5 is equal to 6 EMF divided by 7R. And therefore 3I5, so I5 is 2 EMF divided by 7R. We found I5, we can find I4. I4 is double I5, so it's 4 EMF divided by 7R. So we have this, and finally we need I3. And I3 we can figure out from here. So I3 is I1 minus I4, which is I1 is 3 EMF divided by 7R minus 4 EMF divided by 7R, which is negative EMF divided by 7R. Sorry. What is the significance of the minus? Can somebody help me with this? Why did I get a negative answer? I3. Yeah, I assumed the direction is downwards, but I was wrong. So the answer is that the current is I3 is, well, I don't, so it's the, oh. No, what's the symbol? Greek letters. Oh, okay, epsilon divided by 7R from B to A. So that's the thing. I just need to reverse the direction. Well, my assumed direction was wrong. The answer is still going to be positive. I just need to specify that it goes upwards, not downwards. And initially, if you remember, I said that it's probably going to go upwards because this is a bigger resistor than this. Therefore, the current would steer away from here. Okay, moving on. Okay, so find the potential difference between points A and B in the diagram. Okay, interesting. Interesting. So basically, if we connect a voltmeter here, what will it show? What will it show? And the batteries have internal resistance. So effectively, the batteries have internal resistances, which is R, 3R, 3R, and 2R. 2R. Now, we need to understand that current will flow in this circuit. And so we need to assume the direction of the currents. But we can do quite a good guess. So you can see that this battery is pushing this way. This battery is pushing this. This is the most powerful battery. So it looks like the current will flow this way. The current will flow this way. Now, this is only one sigma, one epsilon, one EMF. This is two EMFs. So basically, if you look at this battery, it's pushing against this battery. And so this battery is unlikely to overcome this battery. Therefore, I'm going to assume that the current goes this way. The current goes this way. And here, well, if current goes in and current goes in, the only way it could go is here. So it can't be the other way around. So I'm going to label them I2, I3, and I1. And of course, I1 is equal to I2 plus I3. And this is where we need to be very careful with the Kirchhoff's laws. So if the current goes this way, so this is plus, this is minus, this is plus, this is minus. Here we have plus, minus, plus, minus. And here we go plus, minus, plus, minus. So choosing a loop, there are three loops here, and why not use three loops? Okay, so let's go around the bottom loop. Bottom loop. So this one. We're going to go clockwise. So the orange loop. We have, so EMF, so it goes from plus to minus. So EMF goes from plus to minus again. So plus I1R. Then we go from plus to minus. So it's plus 3I3R. 3I3R. And then the battery is minus, so it's minus 3 EMF. And that's equal to 0. That's the first loop. The second loop, I'm going to use this one. And it's going to be the red loop. So plus minus. So I'm going to start with the resistor. So it's minus I2 minus 2I2R, because it's 2R. The battery is positive, so from plus to minus, so plus 2 EMF, plus 2 EMF, minus I1R, because from minus to plus, and we go minus EMF is equal to 0. And finally, we can take the green loop. The green loop is the outside loop. And we're going clockwise again. So the green loop. Now we start with here. So this is plus minus. So plus I3 plus 3 I3R minus 3 EMF minus 2 I2R and plus 2 EMF. EMF is 0. Okay. Looks a little bit rough. What can we do? What can we do? Well, we can make our life a little bit easier by replacing I1 with I2 plus I3. So I'm going to go in everywhere where I can. I'm going to replace I1 with I3, with I1 with I2 plus I3. So EMF plus I2R plus I3R plus 3 I3R minus 3 EMF is 0. Okay. I don't want to do any extra steps. So I'm going to write 2. And here it's going to be 4. So it's going to be 4. That looks way easier. And furthermore, I'm just going to write like this. Ooh, beautiful. So from here, I have EMF, so minus 2 I2R plus EMF minus I2R minus I3R equals 0. So once again, making my life slightly easier. So this is going to be minus 3R, 3I2R. So, and I can take EMF to the right and change these to pluses. So EMF goes to one side, this one goes like this, and this. I hope I haven't made a mistake. Now EMF is I2 plus. Really get it. Oh yes, yeah, absolutely, absolutely. And finally, I get this one. And this is EMF. I'll do it right away. EMF is equal to 3 I3R minus 2 I2R. Well, from the second two, it's quite easy. From here, I can say that these two are equal. They're both equal to EMF. So 3I2R plus I3R is equal to 3I3R minus 2I2R. So this is going to be 5I2R is equal to 2I3R. R cancels, and I get I3 is equal to 5I2 over 2. And I can use this here. So I2R plus 20 I2R over 2 is equal to 2 EMF. So that's 10, 11. So 11 I2R is equal to 2 EMF. Okay, so this, I'm not going to simplify this, but this is going to be very useful. So finally, we need the voltage on between points A and B. So the voltage between points A and B. Voltage between A and B is going to be, if basically we go from A to B, we go from A to B like this. It's going to be minus 2 EMF plus 2 RI2. Oh, nice. So I need I2R from here. So I2R is 2 EMF divided by 11, and we're going to use this here. So it's going to be minus 2 EMF plus 2 times 2 EMF divided by 11, which is 4 over 11 minus 22 plus 4 is going to be minus 18 over 11 EMF. Right. Did I? Minus 22 plus 4, minus 11, minus 18 over 11. This is the voltage between A and B. So basically, if you connect the voltmeter like this, it will show you a negative value. Basically, if you want to, if you connect it the other way around, it's going to be plus 18 over 8. So the answer is the voltage between A and B. Well, you could say B and A. The voltage between B and A is 18/11 EMF. So as you can see here, physics finishes somewhere here. So up to this point, this is physics. Everything else is just maths. So and it's always like that in physics. And this is maths. I mean, it would work. It would work if you eliminate I2. It doesn't really matter what you eliminate. It won't work either way. You just need to keep eliminating variables until you get something decent. So yeah, it's just like that. It's if you're completely stuck, try substituting numbers. I mean, a reasonable assumption would be that small r is 1 ohm, and voltage and EMF is 10 volts, and see what you get. And once you get something, you might understand what's going on in the circuit. Okay, and an excellent way to check your answers is using the simulation. FET circuit builder. No, not this one. FET circuit construction kit. So this is absolutely brilliant. It has its limitations, but it's super useful. So what you have is a battery. You can change the battery resistance to 2 ohms. No, I'm not gonna use internal resistance. I'm just gonna use a resistor in parallel because that's the same thing. So one battery goes this way and it has resistance, and another battery goes this way and it has resistance, and it has wires like this, and like this. So this is my circuit, and what I need. So this is the voltage. I'm going to make this is 2 volts. 2 volts. 2 volts. The resistance I'm going to make 2 volts and 2 ohms. And this is going to be 3 volts. And this is going to be 3 ohms. 3 ohms. And this is going to be 1 volt. Can I actually? Can't change it. 1 volt and 1 ohm. All right, so let's see the current. Oh, the current direction is correct. Look at that. We've guessed the direction of the current correctly, and then what we can do is just take a voltmeter and see what we have here. 1.64 volts. Interesting. So EMF is 1, as you could see, as you can see. EMF is 1, and EMF is 1. So the voltage is going to be 18 over 11 times 1, which is 18 over 11, which is 1.64. 64 volts. So my answer is definitely correct. So yeah, do use this. This is an incredibly useful tool. You might have seen it before. Right. What else? There are a few problems here. I'm not sure we can do all of them. I'm going to skip question 5 for now. It's just a lot of maths again. Let's go to question 4. It's quite an unusual one. The battery in the diagram is part of an unknown circuit. So we don't know what's going on with the circuit. It is part of the circuit. So this is, we don't know how it's connected. And but the reading on the voltmeter is 6 volts. Oh, the battery is 4 volts. And it has internal resistance. It has internal resistance. There's no current through the voltmeter. The voltmeters are designed not to have current in them. Therefore, there must be a current flowing. The internal resistance we don't. Oh, the internal resistance. Just a second. Do we know the internal resistance? This is question. It's question 6. 3101. Squared R. Internal resistance is 1 ohm. I forgot to mention. The internal resistance is 1 ohm. Okay. So how does that work? Well, we have the formula for the internal resistance. We know that the EMF of the battery is equal to the, sorry, that's not it. The terminal potential difference. The terminal potential difference is the EMF minus the current through the battery times the internal resistance. And since we know that this is 6 and this is 4, this is minus I times 1. Current is equal to -2 amps. -2 amps. So the current is not flowing right to left, it's flowing from left to right. And because of that, the voltage is more than the EMF of the battery. Because if the current was going the other way, we'd have to do EMF of the battery minus voltage on the resistor. But here, in this case, it's the current flowing this way. So you go plus, minus, so you got EMF plus IR. And then find the rate at which heat is dissipated by the battery. This is the power dissipated on the battery. And the power is I squared R, which is 4 times 1, which is 4 watts. Now, very simple. It's a very simple question. It's just the concept that the current is flowing backwards is quite surprising, but it's that. Let's look at problem. Let's look at problem 7. Look at problem 7. So find the current as it is flowing through the diode. So the diode is, it's a perfect diode. That means that current can only flow one way. Or in other words, if the current flows from left to right, the resistance is 0. And if it's flowing from right to left, the resistance is the resistance is infinite. Right. Okay. So let's say we have this, and I think it's called a bridge. So current will flow this way, and this way, and this way, and we don't know the current that is flowing through the diode, if it is flowing at all. So let's assume that the diode is locked. Assume that the diode is locked, because that's the easy option. Assume diode is locked. That means the diode acts as an infinite resistor. An infinite resistor is equivalent to having no wire at all. So the circuit becomes very simple. There's 1 kilo ohm, of course, 2, and then 3 kilo ohms, 1K, 2K, 3K, and 4K. So if the diode is blocked, this is the circuit. And what we need to do is find the potential difference between these 2 points. But we know that the total resistance, so this is 4, this is 6, so this is 4 and 6, so 4 times 6, so that's our total. 4 times 6 divided by 4 plus 6, oh, that's easy, 2.4 kilo ohms, that's the total resistance. And the total current is EMF, which is 100 volts. Yes, so this, on a diagram, this means the ground. The ground means it is 0 volts. And that means that the potential difference between top and bottom is 100 volts. So this circuit is equivalent to having a battery like this, to having a battery with a 100-volt battery here. This is just using potentials. 100 volts is, and the potential difference is 100 volts. The total current is equal to the EMF divided by our total, and that's equal to 100 volts divided by 2.4 times 10 to the 3. It's not very nice, is it? 100 divided by 2,400. 1 on 24. 24 amps. In A levels, they hate it if you do it like this. So you would answer, you would give the answer in decimals. This is not a correct answer, especially if you're doing A levels. And I'm just going to write it. So 0.41417 amps. So this is the total current, and what else can we do? Well, we can say that the current flowing through the left branch, the current flowing through the right branch. The resistances are 4 kilo ohms the total resistance of the left branch, and the total resistance of the right branch is 6 kilo ohms. So the current will be split in proportion 2 to 3. Current here and current here in proportion 2 to 3. And 2 to 3, therefore, I'm going to call this current 1 and current 2. Current 1 to current 2 is in proportion of 3 to 2. So there's more current through the left branch and less current through the right branch. This is an intuitive approach. You look at the resistance. Of course, you can prove it using Kirchhoff laws, but intuitively, you should understand that if the resistances are in proportion of 2 to 3, the currents will be in proportion of 3 to 2, or the inverse. All right, so the reciprocal. 3 to 2, and we know that the total is 1 over 24, so 1 over 24 divided by 5, 1 over 24 divided by 5, and times 3, it's 1/40th, so I1 is 1/40th of an amp, which is 0.025 amps, and I2 is smaller than that, so it's 2/3 of that value, and so 1/24th divided by 5 times 2, which is 1/60th. 1/60th of an amp, which is 0.0167 amps. That is a bit suspicious because I'm not getting the total. 1/40th plus 1/60th is 124. Oh, of course. Not enough zeros. 0.0417 amps. And then if you add them, you will see that it actually works. So current 1 and current 2. What I need to do now is find the potential. The voltage on the first resistor is equal current times I1. So I1 is 0.025 times 1000. Oh, it's 25 volts. 25 volts. And V2 is 2000 times 1/60th. 1/60th is 33.3. 33.3. So what's going on? So the potential here is 100 volts. The potential here is plus 75 volts because there's a potential drop from this point to this point because the voltage on this resistor is 25 volts. The voltage on this resistor is 33.3. So we've got a 66.7 volts potential here. That means that the potential at this point is bigger than the potential at this point. That means the diode cannot be locked. Potential at A and B. So potential at A, V at A is greater than the potential at B. That means current will flow from A to B, so the diode cannot be locked. So our assumption was incorrect. So now we have to assume that the diode is unlocked. That means assume diode is unlocked. And this is going to be very similar to the very first question. Not the first, the third question, I guess. Diode is unlocked. Now we have current flowing through here. Now you need to understand that the circuit is going to be like this. So this is like a single point. It's a series connection of two parallel connections. So this is going to be 1, 2, 3, 4 kilo ohms. So the total resistance of the top two. So our total is equal to the total of the top two is R 1 times 2, so it's 2 divided by 3, 2/3 of a kilo ohm, and plus 3, so that's 12/7 of a kilo ohm. It's not nice. Is it though? Yeah, so we got R1, R2, yes, 12/7. So that's 14 plus, so that's 14 plus 14 plus 36 sevenths. That is 57 kilo ohms. 57 kilo ohms. Now we need the current through this branch, and we know that the voltage on V1, it's called V1, is equal to V2. Oh yes, of course, sorry. 50, 20, 21st. So the current I0, let's call it I0, is equal to 100 volts divided by 50 over 21 times 1,000. So that's 42 thousandths of an amp, which is 0.042 amps, or 42 milliamps. 42 milliamps. That's the current I1. Then we need to compare the currents. So we need to say, okay, so the voltage V1 is equal to V2, because if you put a voltmeter here, across this and the voltmeter here, it's going to be the same. So V1 is going to be equal to V2 because they are in parallel. So I1 times 1,000 ohms is equal to I2 times 2,000 ohms. In other words, I1 is double that of I2. So 42 split in proportion of 2 to 1. So 42 divided by 3 is 14. So here we are going to have 28 milliamps. And here we're going to have 14 milliamps. 14 milliamps. Therefore, if you have 28 and 14. Now let's look at the proportion of the third one. So V3 and V4. So V3 is equal to V4. That means that I3 times 3 is equal to I4 times 4. So 42 milliamps we need to split in proportion of 3 to 4. So that's going to be 18 milliamps. So this is 18 milliamps, and this is going to be 24 milliamps. 24 milliamps. Okay, and looking at that, so this must be 4 milliamps. 4 milliamps. So we're going back. So what we have here is we assume that the diode is closed, and we've drawn the circuit like this. And then we saw that there is a contradiction because the potential at this point is bigger than the potential at this point. And in this case, the current would flow from left to right. And here we just do that. Okay. You could have done it straight away from here and saw that there's no contradiction, therefore the diode is open. Any questions? Right. I hope it's not overwhelming. Like honestly, I think the questions in the assignment are easier than what we're doing now. Honestly, assignment 7 is much easier than assignment 6. So assignment 6 was genuinely difficult. Okay, problem 8. Problem 8. So what have we skipped? We skipped problem 5. Oh, we just skipped problem 5. Yeah, let's go for problem 8. Problem 8 is not a difficult one. You just need to consider 2 options. So you have R1, which is 30 ohms. You have R2, which is 60 ohms. And you need the total resistance when the current is flowing from A to B. Well, if current is flowing from A to B, then the diode has 0 resistance. So from A to B, this is 0 ohm. In the circuit, so from A to B, this is option A. The circuit becomes like this, R2. I'm just drawing an equivalent circuit, which is R2, R2, oh. Sorry. Just draw the equivalent circuit. So this is like this, R1, resistance, R1, like this, and R like this, and this. R1, R1, R2, R2. So what do we notice here? So Well, to do this question, I'm going to 20 ohms. So it's a perfect diode. The perfect diode has 0 resistance in the forward direction. And it has infinite resistance in the backwards direction. So it's 20, so it's 30, 60. Okay, so it's not that easy as I initially thought. So let's connect it like this. Let's connect it to a battery of EMF E. Okay. And because R2 is 60 ohms, I'm just gonna make my life a little bit easier. I'm gonna call this R. This is 2R. This is 2R and R. This is 2R and R. So I need a current, I0, and I have I1, I2, I'm gonna assume the current is going like this, I3, I4, I5. Horrible in a way, but and then we have go back to I0. So we label the currents. So write out I0 is equal to I1 plus I2. I2. We have I0 is also equal to I4 plus I5. And we have I5 is equal to I2 plus I3. So using Kirchhoff's laws, Kirchhoff's first law, the current law. I only did it for 3 junctions, but okay, for completeness, I'm just gonna write I1 is equal to I3 plus I4. This is for this junction. Finally, what can I do? I write Kirchhoff's second law. Kirchhoff's second law that EMF is is I4R. I4R, because we can make a loop that goes like this. EMF is equal to I4R. Then we can say that EMF is equal to 2I3R plus I5R. And interesting. If you take these two, you can see that the potential difference between these 2 points must be 0. So basically, these two resistors, this one and this one, they are in parallel. So I2 times 2R has to equal to I3 times 2R. In other words, I2 is equal to I3. Oh, and that's a lot of help. I2 is equal to I3. And that's a great discovery. So I1 is I3 plus I4. Can we do something similar to this? Well, not really. I2 is equal to I3. I1 is I2 plus I4. Well, okay. Can we do the total current? I guess so. I2. Oh, if I2 and I3 are the same, that means I5 is 2I2. That's going to be useful. And I4, I1 is equal to I4 is I4 plus I3. So I have this, I4 plus I3. Can I use this? Well, not yet. Let's say, let's find I0. I0 is going to be very useful. So the total, oh, if we find I0, we'd find the total resistance, of course. So we need I1. I1 is I4R. So from here, I4 is equal to EMF divided by R. And for simplicity, I'm just going to use, no, it's fine. So I4 is EMF divided by R, which is going to be useful. So we also have that I3 times 2R plus I5 times R is equal to I4 times R. I4 times R. And oh, we already have this. Sorry, we already have this here. But anyways, and we are almost done. So I3 is I2. So I2 times 2R plus I5 is 2 I2R is equal to I4R. And in other words, I4 is 4I2. 4I2. Brilliant. Is 4I2. I'm just going to label this. So I2 is I3. I3 is I2. This is 4I2. This is 2I2. So I0 is 6I2. And this is I2, of course, and I1. So this is I2 and this is 4. I1 is 5I2. I4 is 5I2. Oh, that doesn't make sense. That's I2. Oh, 6. Yeah, 6. I0 is 6I2. Okay. So the total resistance is going to be EMF divided by the total current, which is I0. EMF divided by total resistance. So EMF, and we know that EMF is EMF is I4R. I4R. And we know that I0 is 6I2. And we know that I4 is 4I2. So this is going to be like 4I2R divided by 6I2. Cancel. So it's 2/3 R, and R is 30, so it's 20 ohms. So, right, 20 ohms. Okay, quite messy. Do take your time to dive deep into this and actually figure out why it's 20. But the other option is much easier. So going from A to B. Now we're going from B to A, and this will be much faster. So B, we're going from B to A, so current is flowing from B to A. That means that the resistance of the diode is infinite. So current is not allowed to flow backwards through the diode. So the circuit becomes much simpler. We've got R2, well, 2R, yeah, because it's 60. 60, then we have R2, so 2R, then we have R, on the bottom we have R, and well, that's it. So this is 3R in total, this is R. So the total resistance, R total, is going to be 2R, so it's this resistor, plus the resistance of this combination, and the resistance of this combination is, if you're not confident with this, do practice. This will really help you solve problems quickly. 2R plus, oh, right. Okay, my pen went a bit crazy. Sorry about that. Right. I'm very sorry about that. So can't do anything here. I think that's the nature's way of saying we should stop. But I mean, the total resistance is going to be 2R. I can't even type 2R. I'm very sorry for the technical disruption here. I'll fix this. It's going to be 2R plus 3R times R, so 3R squared over 3 plus R, so it's 4. So it's going to be 3/4 of R. So 2R plus 3/4 of R. That's going to be 2R plus 3/4 of R. This is going to be 2 plus 0.75, 0.75. So it's 11/4 times 30. It's going to be 82.5 ohms. Okay. We'll finish here. If you have questions, do ask me. I'll try my best to answer, even though it looks computer just went. Any questions? Well, I'll see you next week then, if there are none. Welcome.